All right. Okay, so before I introduce Grant, I want to remind you of the community statement. So the sort of three principles here are that we're all learning, everyone has something to contribute, and no one has all the answers. Okay, and so without further ado, we're very happy to have Grant Barkley telling us about extending the weak Bruhat order.
Thanks, Sarah. Yeah, so feel free to interrupt me at any time. So yeah, I'm mostly going to be defining things in the beginning, and then I will start talking about how exactly we'll extend the weak order. Okay, is that visible for everybody? Cool. Okay. Okay. So where are we scrolling? There we go. Okay. So first of all, so my talk is called Extending the Weak Bruhat Order. So I wanted to remind everybody first what exactly the weak Bruhat order is. This is probably most familiar in the context of the symmetric group. So the weak Bruhat order is a partial order on the elements of the symmetric group or any Coxeter group. I'm not going to define Coxeter group, but I'll give you several examples. So for the symmetric group S3, this is the partial order. This is the Hasse diagram of it. So at the bottom, we have the identity permutation, and at the top, we have the permutation that reverses everything. And we kind of have two chains going up from the bottom to the top. So we'll see this picture in like 8 different variations throughout the talk. So we'll kind of see a bunch of different perspectives on what exactly this order is. It'll probably be like 10 minutes before I actually define it. But I can at least tell you how I wrote down this specific Hasse diagram. So the idea is that the symmetric group can be realized in kind of a geometric way. So we can describe the symmetric group as the symmetry group of a simplex. So this is like, a triangle, a tetrahedron, and whatever the higher dimensional versions are called, the n simplex. So as a special case of this, the symmetric group S3 is the symmetries of a triangle, a regular triangle. And so I've drawn a picture of a regular triangle, and I've labeled its vertices 1, 2, and 3. And the various permutations of 1, 2, and 3 realize the different symmetries of the triangle. And the structure that I want to highlight is that certain, was there a question? Okay, that certain of these symmetries actually are reflections, reflective symmetries. So for instance, the transposition 1, 3, which swaps the vertex labeled 1 with the vertex labeled 3, is the reflection over this line. And similarly with 2, 3, and 1, 2. So reflections correspond to kind of like distinguished elements of the symmetric group. And this is a general phenomenon for Coxeter groups. And we'll kind of see some of the structure relevant later on. So I'm going to forget about the triangle for now. We won't be looking at triangles, but there's like a nice theory of like polytopes that have symmetries generated by reflections, but I'm not going to talk about any of that. So from now on, we'll just be interested in these lines of reflected symmetry. So this collection of lines is called the Coxeter arrangement for S3 in this picture, or Sn in general. And a more familiar term to you might be the phrase braid arrangement. So this Sn Coxeter arrangement is the braid arrangement on however many letters. And we'll see, again, many pictures of this later on. Okay, so now I can define the weak order, at least in the case of S3. So there's like a couple of different statements here. So let me break this down. So first, we're going to pick a permutation. So let's say I pick the permutation 2, 3, 1. Okay, and I say here, let R sub W be the region associated to W. Okay, what does that mean? First of all, region of what? So our Coxeter arrangement, which is shown here in the bottom right, splits all the space up into various regions. So the regions are these like triangles here. So that's a region, this is a region, that's a region, that's a region, that's a region, and that's a region. So our Coxeter arrangement splits up space into regions. And when I say the region associated W, I just mean if we kind of if let's say we take a vertex here and we act with the symmetric group on this space, we look at where this vertex gets sent. And there's a couple of different ways of realizing this. So as a special case, for instance, like 2, 1, 3 would correspond to this region, 2, 3, 1 would correspond to this region, 3, 2, 1 corresponds to that region. And you can kind of look, I've given out inequalities describing these regions on the right. So this triangular region is the region where you have your coordinates are strictly increasing. Here we've swapped the second and first coordinate, so the second coordinate is bigger than the first coordinate, and both are less than the third coordinate. And again, you kind of see the correspondence between the left side and the right side. The permutation 2, 3, 1 goes to the region given by the inequalities x2 is less than x3 is less than x. Okay, so that's the first line here. And now kind of like really short definition of the weak order on the symmetric group is we say that two elements of the symmetric group are V is less than or equal to W in the weak order if, oh, whoops, I never defined this S thing. If the lines separating this region corresponding to V also separate the region corresponding to W. So let me talk about this, sorry. Okay, so this separating set is the set of lines separating the region from the region at the bottom, so the region corresponding to the identity permutation. Okay, so for instance, for our example of the 2, 3, 1, the set of lines separating this region from this region is this line and this line. And so that's just a collection of the lines in the picture. Okay, and now we can define weak order to be containment of these separations. And now you can kind of see where this picture on the left comes from. As we go up along this side, we're adding one line at a time to our separating set. So first, as we go from the bottom to here, we're crossing this line. So this line's added to our separating set. Then as we go to here, we're crossing this line. So that's added to our separating set. Then we go here and we're adding this line. And you can do the same thing on the other side. So this partial order corresponds to these like separation sets. And so there's a nice like visual interpretation of what this partial order is. Okay, any questions about that before I start talking about other Coxer groups? Okay. So the symmetric group I said was a special case of a Coxeter group. And in general, a Coxeter group is some sort of group that always has this nice realization as symmetries involving reflections. So here I've drawn the like lines of reflective symmetry for various different Coxeter groups. So if I remember correctly, this one is called A2 tilde, this one is called B2 tilde, no, wait, I think that's called C2 tilde. And then this one is called like the universal Coxeter group on 3 elements. But as you can see, like the pictures kind of get a bit weird compared to what we were looking at before. So now there's like infinitely many lines. These pictures keep going on beyond the borders that I've drawn here. And we can even have these like non-Euclidean reflections, like in this case. So this is called a hyperbolic Coxeter group. So there's like a lot of like interesting and complicated geometry that can happen. I'm going to focus on things that look like this. These are called affine Coxeter groups because they correspond to affine reflections, by which I mean like reflections over lines in affine space. Okay. So to talk about the constructions that I want to work with, so to define weak order in full generality and then to extend it later on, it'll be convenient to work with normal vectors to our reflecting hyperplane. And so I've drawn in black again the Coxeter arrangement for S3. And I've also drawn a collection of normal vectors to those hyperplanes. So for instance, like this line has this normal vector and this normal vector. Every line has 2 normal vectors. Okay, and then I've also labeled them. So this one's called alpha 1, this one's called alpha 2. This one is the sum of those two. And it turns out that this particular set of vectors is particularly nice. It's something called a root system, which I'll define on the next slide. But the idea is just that as a set of vectors, it's highly symmetric. It's as symmetric as the original arrangement of hyperplanes was to begin with. You can kind of see that here. Like if I had chosen this normal vector to be twice as high as all the rest, it would not be as symmetric. So, oh yeah, is there a question?
Yeah, so on the previous slide, you're showing examples of hyperplane arrangements that were affine. So do root systems interact well with these affine reflection hyperplanes?
Yeah, that's a great question. And so, yeah, the reason that, yeah, so it'd be really hard to write down, I mean, yeah, it would, so if I were to like naively write down normal vectors, right, they would be kind of not vectors, they'd be kind of like centered at various places that are not the origin. But the reason is because I've just drawn this. This is really, each of these is really a three-dimensional picture that I've taken a 2D slice of, like an affine slice of. So you would actually look at all of these lines are actually planes through the origin, and then you can look at the normal vectors of those. Yeah, and then it works the same. Okay, so here's the actual definition of a root system. It won't be important to remember. The key takeaways are the following. So we're going to have a set of vectors. So we have a set of vectors alpha 1 through alpha n. That's a basis. We're just going to start with this like basis for our vector space. And so this basis for, oh, I don't think I said it anywhere. V is just a real vector space. And then we've chosen a basis for V, and we call those the simple roots. Okay, we've also defined a bilinear form on here. I'm going to ignore that for a second. You can just assume it's Euclidean for the moment, like the usual inner product. Okay, so we're going to define a root system to be a subset of our vector space, which contains this basis, and such that if we have any two, well, I guess first this statement is really two statements. So first, if we have any element of our root system, then its pairing with itself is positive. So if we have an inner product, that'll be true for any non-zero vector. So that condition is automatically satisfied. But eventually we'll want to look at things where this is not an inner product, where it's just bilinear. So we want to ask that this is always true. And then furthermore, if we take any two roots in our root system, and we reflect one root over the other, then we get a new root in the root system. So what do I mean by reflect one root over another? Well, whenever you have a bilinear form and you have a vector such that its pairing with itself is non-zero, then you can define a reflection operator on your vector space called like orthogonal reflection over your vector, which does this. So this is just the formula for reflection over alpha. And it sends any vector to that vector minus this formula. And if you have a usual inner product on your space, this coincides with the usual like orthogonal reflection formula. So this is just a literal exact the same formula, but with a bilinear form instead of an inner product. Okay. So this condition is the one that tells us that our set of normal vectors is highly symmetric. And then there's one other condition that is really what makes a root system, but I'm not going to focus on too much. And what it says is that if we expand any of our roots in our chosen basis from right here, then all the coefficients are either non-negative or all the coefficients are non-positive. So one or the other happens. You can't have alpha 1 minus alpha 2 in your root system. Okay, and we'll talk about why we want that in a second. Okay, so here's again, this is the same definition. Let's look at the special case of the root system for S3 that I had drawn a couple slides ago to motivate this. So I have my basis vectors are alpha 1 and alpha 2. We also have the sum of those two things in the root system, and then we have the negations of all of those roots. And you can check that if I do orthogonal reflection over any of these roots, then that reflection will take one root to another. And we also have this third property. Yeah, so this third property basically just says that we don't have something like alpha 1 minus alpha 2. Right, we either have, yeah, all positive combinations or all negative combinations. So we can actually kind of split this picture in half and look at just the positive things and just the negative things. So those things that have a positive coefficients and those things that have negative coefficients. And in fact, this is where we do that. So when we do that, we call those things with positive coefficients the positive roots. And then, yeah, question in the chat, negative alpha 1 is the reflection of alpha 1 over itself. Exactly, yeah. So for any vector, if you reflect it over itself, you'll just get its negation. Okay, so the positive roots are kind of just half of the root system. Okay, and then for any root system, we can define a GOCC arrangement. So this is just the set of all hyperplanes that are dual to the vectors. So just kind of going in reverse from what we were talking about before. And we can also define a group associated to any root system. So in this context, it's called a while group. So when you start with a root system and build a group, you usually call it the while group of the root system. There's actually a way of starting with a group and building a root system, but we don't really need that. So the while group is just the group generated by all those reflections over every root in our root system. Okay, so let's take a look at, oh, I thought I had a symmetric group. There's a, okay, well, I'll get to that in a second. Okay, so yeah, this is the same definition. We can also look just at the reflections over our simple roots. So this basis for a vector space. There's much less of those, only n of those, whereas your root system itself could be infinite. It turns out that those reflections over the basis vectors already generate W. And they're called simple generators or simple reflections. And then this pair WS is something called a Coxeter system, which is what makes W into a Coxeter group. Again, not going to define that, but this is like a really important theorem and like the theory of reflection groups in root systems. Okay. Now let's define the weak order for an arbitrary Coxeter group. So first of all, I'm going to define what is called the inversion set of an element. So for permutations, this will turn out to coincide with the usual notion. And so what it is I take all of the positive roots for which are sent to negative roots by W inverse. So positive roots that get sent to negative roots by W inverse. And the inverse here is just a left-right thing. It's not a big deal. Okay, and now the weak order on our group is the partial order given by containment of inversion sets. Okay, and so this last thing that's getting cut off is explaining the connection between this notion in terms of roots and the notion we were looking at for the symmetric group. So when we defined the weak order for the symmetric group, we looked at regions of the Coxeter arrangement. And then we looked at the lines or the hyperplanes that separate that region from the region corresponding to identity. And so what is the connection between these two things? Well, this collection of all hyperplanes that separate the region from the identity region is actually just the set of all hyperplanes orthogonal to the roots in N of W. And so that's what this bottom part says. Okay, so the correspondence between the N and the S is just vectors versus their orthogonal hyperplanes. Okay, so let's look at the symmetric group. So we've already looked at the S3 root system a lot. So let's do a more general setup. Okay, so we can define the root system inside R to the N with the usual inner product and an orthonormal basis. So if our orthonormal basis is these EIs, then we can define a vector called alpha ij, which is defined to be EI minus EJ. So just the difference between our basis vectors. And in order to define a root system, we need simple roots. So I'll define the simple root alpha I to just be alpha I comma I plus 1. And then the span of these simple roots is not all of R to the n. It's a codimension 1 subspace. So we just define the vector space our root system lives in to be that subspace. And then our root system is just these alpha ij's. Okay, and so if we define a root system in this way, then, and we look at the reflections generated, we look at the group generated by the reflections over these roots, it turns out that this group is isomorphic to the symmetric group. And the reflection over the root alpha ij is just the transposition swapping I and j. So this is a generalization of the thing we saw for S3. Okay, sorry, any questions on that? I'm about to kind of change topics. So this was, yeah, just the introduction to the weak order. Any questions about these definitions?
Hi, can I ask a
Yeah.
question?
Yeah, what's up?
Hi, so between, in your picture, between the permutation, we have the faces, which are parameterized by surjection or set composition, if you want.
Mm-hmm.
So this is a naive question. The symmetric group is the Weil group. Now, set composition are not a group, at least not with composition, but is there in the theory of Coxeter groups some algebraic structure which relate geometrically the set of faces in the same way that you can say that the Weil group of phi is the symmetric group? So is there something in the Coxeter theory of Weil theory which say, so this thing is now geometrically associated to the set to the faces, the set of faces of the hyperplane arrangement in this case?
Yeah, so that's a good question. So here's the thing that I'll generalize. I've mentioned a couple of times that at least for the symmetric group, there's a bijection between the regions, which are like the maximal faces of our hyperplane arrangement, and the elements of the group. So in particular, there's like a group structure on those, but and then you're asking, okay, what if we consider also these like lower dimensional faces, like maybe like for here. So like for instance, this arrow right here is a lower dimensional face corresponding to so this is I'm not going to try to figure that out. So the answer is that these faces actually correspond to something called parabolic quotients. So or equivalently parabolic subgroups. Oh, actually, so maybe more naturally, the correspondence is like, I guess one more thing, parabolic cosets. So there's a bijection between something called like parabolic cosets and faces.
Thank you.
Yeah. No problem. I can talk about that more after the talk.
Yeah.
Okay. So, all right, the weak order is great. We've now seen it defined a couple of different ways, and in a little bit we'll also see some more pictures once I set up a new framework for describing the weak order that's a bit more geometric. So I guess we already have one geometric way of seeing the weak order, which was this like separating set, the set of hyperplanes separating one region from another. And then we also have this like notion of an inversion set where the definition, I mean, unless you're used to it, it doesn't really seem how like it connects to that in any obvious way. So let's see if we can come up with a root definition of weak order that is geometric and also easier to understand. And so the way that we'll do this is something called biclosed sets of roots. So biclosed sets are something that you can like just define very generally. Second. So if we have a vector space and we have a set of vectors in that vector space, I've denoted it phi plus because it'll end up being positive roots. Then if we take a subset B of phi plus, Then there's two different properties. Okay, sorry. Then we call it a bi-closed set if it satisfies two properties. One is called closed and one is called co-closed. Okay, so both of these properties relate to triples of vectors such that one is in the positive span of the other two. Okay, so if gamma is in the positive span of alpha and beta, then the closed condition says that if alpha is in B and beta is in B, then gamma is in B. And the co-closed condition says that if alpha is not in B and beta is not in B, then gamma is not in B. So another way that you could define these terms is you could call co-closed, instead of calling co-closed, you could call it open, because all co-closed is saying is that the complement of B is closed. And then bi-closed, you could also call this like clopen. However, for whatever reason, this is just not the terminology used in this area. Okay. So we just have this kind of like vector definition of bi-closed. Let's take a look at what this looks like for our favorite example, this S3 root system. Okay, so if we do that, we'll see that first of all, if you just take all of the positive roots, that's a bi-closed set. Certainly it satisfies this condition, and then the complement's empty, so this condition is also good. Okay, and I'm going to start to let's look for some like counterexamples. So if I tried to take alpha and beta without having alpha plus beta, then this fails the closure condition because this is in the positive span of this and this. So since these two things are in a set, if it's to be closed, then it also needs to have this. Okay, so this set is not closed. And similarly, this set is not co-closed because it violates the co-closed condition. Okay, so let's just write down all the bi-closed sets, and I've kind of drawn them in a certain positioning that may seem familiar. So let's look at the inclusion order on these things. So here's the Hasse diagram for the inclusion order on these sets. These are sets of vectors, so we can just look at containment order. Okay, yeah. Any guesses for what this poset is?
The right weak order.
It is, yeah, it's just the weak order. That's all I was going for. Weak order on S3. Yeah, don't worry about right versus left. I'm sure I've like swapped those at some point. That's, yeah, I'm not going to be saying anything meaningful about left versus right.
I did actually have one quick question though.
Oh yeah.
Before we move on, can I understand bi-closed as it's the intersection of your set with some cone, or some convex
yeah.
cone?
So, so the bi-closed the closed condition is saying that if you take the cone spanned by two of your vectors, then any other vectors in there must also be in the set.
Okay.
Yeah.
Yeah, that'd be the closed condition, not the bi-closed condition. That would be
right. And then the bi-closed says that like if you have two things that aren't in your set, then nothing in between them can be in the set. Yeah. There's actually a more general version of this, not more general, less general version of this called biconvex. That turns out to be bad, but this is just the condition that like if you take the cone over your set, then everything inside the cone is also in the set. This turns out to be bad. Okay, so as Mark pointed out, this was the weak order. So what is the correspondence between these things? Well, let's remember the original way that we defined the weak order. So if we're looking at this element, we know that 231 is bigger than 213 because everything separating 213 from the bottom region also separates this region from the bottom region. Okay. So if we think about containment, let's see, let me actually write stuff. So let's say this is 1, 2, this is 2, 3, and this is 1, 3. Then the separating set here is the set 1, 2, and the separating set here is the set 1, 2, and 1, 3. Okay. And if we look over here, this vector is the normal vector to the hyperplane 1, 2. So this plane well, line, I guess. This line, this is its normal vector. And here, our two separating things were 1, 2, and 3. So these two things. And here, those are the two normal vectors. So you can see visually what the correspondence between these biclosed sets and our original like separating set notion of weak order are. And so this suggests the following theorem. Maybe not the way that you would have guessed it's phrased, but the theorem due to Matthew Dyer is that if and in the finite type case, a couple of other people as well. So if phi is a root system, then the inversion sets are for, so like the inversion set of a group element W. Oh no, that's not right. Sorry. The collection of inversion sets of all of the elements of your Coxeter group are exactly the finite biclosed sets of positive roots. So there's like a bijection between finite biclosed sets and these inversion sets, and it preserves containment. Okay, and then there's also one more bijection is, so if phi is a finite root system, then both of these things are also in bijection with the regions of the Coxeter region. So that's the observation that we've been using. Okay, so here's just the same pictures. We've pretty much already seen this. So notice that our root system only has three positive roots. So all the biclosed sets are finite because they're always a subset of this 3 element set. So maybe something more interesting happens. Why would I have included finite if something more interesting doesn't happen in the infinite case? So we'll see that in a second. So this is our first example of an infinite root system. Okay, so I've just kind of defined it. So first we fixed it's going to be in a 2-dimensional space. We've fixed the basis alpha 1 and alpha 2. I'm defining this vector. It's not actually going to be a root for our purposes. And what we do is we just take all translates of alpha 1 and alpha 2 by this special vector called delta. Okay, so I've drawn the positive roots in the picture on the left. And as you can see, I guess it's somewhat like the A2 root system, except it keeps going up and up and up. Okay, and the wild group of this thing is isomorphic to the free product of 2 Z-mod 2s. And it's generated by, so like each Z-mod 2 is generated by reflections over one of these 2 simple generators, simple roots. Okay, so we'll be working with that for a little while. So let's look at the weak order for this thing. So we have a couple of ways of describing this. We can either use inversion sets, and then we get this picture. We can look at finite biclosed sets, which turn out to actually be inversion sets by that theorem of Matthew Dyer, in which case we get this picture, which is, I think, a lot more clear geometrically. And I want to compare this to the Coxeter arrangement picture in a second, but first, just to be clear, like this poset, you can go off to the left and add these like translates by delta one at a time, up and up and up, and you can do that infinitely. And then you can do the same thing on the right, but these things never come back together at the top. Okay, now how does this relate to the Coxeter arrangement? Well, so here, separate. Oh yeah, yeah, I guess so, based on the way I wrote the words here. Okay, so here is our vectors. I'm just kind of copying the picture on the left. Okay, so as you can see, if I just keep tracing along this Coxeter arrangement and filling in these finite biclosed sets, I'm never going to reach the midline of this picture. I'm just going to keep getting infinitely close to it. So we can kind of say that the finite biclosed sets only cover the bottom half of this picture. Okay, so we can already kind of see why we might want to extend the weak order, the title of the talk. Maybe we want to actually see all of these regions. Yeah, Zeno wins. And so we're going to want to, break Zeno's rule, and we're going to want to somehow get beyond this limit wall at infinity and see these other regions back behind it. And so that will be one of our, at least that'll be our geometric motivation for extending the weak order. And then I'll talk a bit about more of the algebraic reasons that we want to do this as well. So one of those algebraic reasons is the following. Oh, so this in the middle, I have not defined this root system, but there's the B2 root system. Here are its positive roots. And then this is the weak order for that root system. So the reason that I've drawn three things up here is because so far we've only seen one example of a finite root system and one example of an infinite one. So here's another finite one. There's some properties that they have in common. Well, they both kind of look like circles is one. The property that's going to extrapolate and continue working in higher dimensions is the following. So it's a theorem due to, okay, so this first thing is the theorem due to Bjorner, Elderman, and Ziegler, and then the second sentence is a theorem due to Bjorner. And the theorem says that the weak order is a poset theoretic lattice, meaning that it has least upper bounds of any collection of elements and greatest lower bounds for any collection of elements. So that's a nice property for a poset to have. And so our weak order has this property if and only if our Coxeter group was finite, or our root system is finite. Same thing. Okay, so in this case, that's these two things. You can see that any, say, pair of elements has a least upper bound. So here that's this, and it has a greatest lower bound. So here that's this. And then same thing in here. Okay, and this is not a finite root system, so this should fail to be a lattice. And the thing that it fails to do is have a common upper bound for these two elements. So there is nothing up here which is a common upper bound for those two elements. However, there is a greatest lower bound, which is this. So Bjorner proved that this order is always a meet semilattice, meaning that there's always greatest lower bounds. Okay, so algebraically speaking, we would like to have a lattice. I predicted this before the talk. I'm starting to lose my voice. I apologize. Okay, so yeah, we could ask what happened to the top half. So if we had pictures that look like the finite type pictures, then there should be some element at the top here, which should be the join of these two things. And if we just think about the Coxeter arrangement, we knew that we could not escape this limit wall. But if we could, then we'd have this region up here that would satisfy our constraint for being the least upper bound. So it'd be nice if we can do that. And so here finally is the definition of our extended weak order. So the extended weak order on the group is the poset of all biclosed sets, not just the finite ones, all biclosed sets under inclusion. Okay, and so here I've drawn the extended weak order for this A1 tilde, the infinite root system that we've been looking at. So highlighted in green are the finite biclosed sets, and everything else is an infinite biclosed set. And so now we have very satisfyingly defeated Zeno because as we continue adding one vector at a time to our set over and over and over again, eventually we get to a set which is just the union of all of those sets, which is infinite, but that's fine. It is a biclosed set. And then similarly, if we start with the set of all positive roots, then that's a biclosed set, and we can subtract one root from it one at a time and go back down. And again, if we take the intersection of all those, we get this again. So as part of what I just said, this union and intersection thing is actually telling us that not only is this thing a lattice, it's actually a complete lattice. So that means that we can take these like increasing joins, and we can take these decreasing ones, even of infinite families. Okay, and so now the question is, does extended weak order just solve this problem of like whether things are a lattice or not? And so, I mean, that's a good question. That's what part of my talk is about. So this was conjectured by Matthew Dyer, who's also the person who introduced biclosed sets and done most work with them. So he conjectures that extended weak order is always a lattice for any Coxeter group. So for finite Coxeter groups, we already know this. But outside of finite Coxeter groups, not much is known. I'll talk about what is known in a second. But one of our goals, me and David Spire, who I was working with on this, is to solve this. Okay, so what do we know? So first of all, there's this powerful theorem by Bjorner, which is that the finite biclosed sets are a meet semilattice. So this is the weak order. So for finite Coxeter groups, this just implies that extended weak order is a lattice because it is the same thing as the weak order, and we know the weak order is a lattice. Okay, so that covers finite type Coxeter groups. Wei-Xiao Wang, who was a student of Matthew Dyer, proved that the rank 3 affine root systems, so the 3-dimensional ones, also satisfy this conjecture. So that's the first time that a non-trivial infinite root system was shown to satisfy. So you can also show pretty easily that this A1 tilde that we've been looking at is a lattice. We basically did that when we were looking at the picture. Okay, and then so I have not defined what an affine root system is. I know it's not even worth reading this. We saw an example. They're the simplest infinite root systems. And so with David Spire, we've shown a lot of different classification results and various structural properties of biclosed sets for affine root systems. So one of those results is that you can kind of figure out the asymptotic behavior of a biclosed set using the geometry of the Coxeter arrangement of the finite type root system associated with your affine root system. I'll get into that, but it is related to the question that I think Yannick asked. And then we've also given explicit combinatorial models for the biclosed sets in the quote unquote classical affine types. So these are the affine Coxeter groups for which we actually do have combinatorial descriptions. So they're the only ones that it could be reasonable to have combinatorial descriptions for the biclosed sets of. And we do have these explicit combinatorial models, which are pretty nice. I'm almost out of time, but I do have some slides about how to see one of these, at least in type A. But they're in terms of total orderings of the integers, and you can kind of just see what's going on very nicely. I probably won't have time to talk about that, but the paper is on the archive if you'd like to see those descriptions. And then, of course, finally, we have actually proven that Dyer's conjecture is true for affine root systems. So if we have an affine root system, then the extended weak order is a complete lattice. So this is extending Wei-Xiao Wang's result for the 3-dimensional ones. We've done it for every dimension. Okay, and then I stop at 750, right? Oh, 150, sorry, I'm in France.
Yeah, we started a little bit late, so if you want to go for 5 more minutes, I think that's fine.
Okay, sure. Yeah, this is a cool example, so I'll just do this and then stop. Okay, so let's talk about a combinatorial description of biclosed sets for the infinite symmetric group. This is not really an affine Coxeter group. Some people do consider it to be, but I mean, I don't really. However, it is an infinite Coxeter group, so we can still do the same constructions. So this is defined to be the group of permutations of the integers which fix all but finitely many points. There's a root system in an infinite dimensional space, which you can, this is the wild group of that root system. Okay, but we don't need to know that. I claim that the weak order on this infinite symmetric group is not a complete lattice. And now why is that? So here I have listed a sequence of permutations of the integers fixing all but finitely many points. So elements of this symmetric group. And each one, as we go down the sequence, moves 0 further to the left. So 0 is getting inverted with more and more elements of the sequence. And so if we wanted to take the join of this sequence of permutations, we might expect, you can just picture this as a limit. If we take the limit of this sequence, we might expect that 0 just goes over here to the left of all numbers. Okay, so if we look at this picture, the issue is that this is not a permutation of the integers. If it was a permutation of the integers, what exactly number is going to 0 here? There's no number that's less than all of the numbers. So it's not a permutation, but it is a total order of the integers. We can still look at this picture and make sense of it. So why don't we just think about total orders of the integers and see where that takes us? And so here's some theorems. So biclosed sets for this infinite symmetric group can actually be identified with the total orders of the integers. So every total order of the integers gives you a biclosed set and vice versa. Which means that the extended weak order of the symmetric group is just like the natural definition of a weak order on the total orders of the integers. Okay, so let me denote this coset by the tot of z. Okay, so we can prove the tote of Z is a complete lattice. This is actually not too bad. So it's if you've ever proven that the weak order for the symmetric group is a lattice, it's exactly the same proof. So I challenge you to do that at home. It would not be yeah, the best way to learn it is to try to do it. Okay, and then I'm going to skip this part, but you can actually use this description of biclosed sets in the infinite symmetric group to learn things about this these affine Coxeter groups. So I'm going to skip this and this and skip to here. Feel free to look at my slides later if you want to see how to do that. It's also in like the paper. Wait, is it in the paper? It's in, yeah, it's in the paper. Okay, so here's some remaining questions and conjectures, and there's a lot more than what's listed here. So in finite Coxeter groups, the weak order is a semi-distributive lattice. And what that means is that every element has kind of a canonical factorization using like the join and meet operations into elements that are join irreducible or meet irreducible, depending on what you're doing. So it's kind of like a unique factorization domain, but for a lattice. And so the question is, does the analogous statement hold for the extended weak order? We really have not proven anything about the extended weak order other than that it's a lattice or affine type. So maybe somebody could use those explicit models that we have to try and prove this. And so another problem is, and this was one of our motivating projects, I guess, one of the things we want to apply these biclosed sets to understand is there's something called a Cambrian lattice, which generalizes the Tamari lattice, which is like a lattice structure on the icosahedron vertices. And the reason that you would want to construct these generalizations is because actually they relate very strongly to the geometry associated with cluster algebras. And there's even a like combinatorial setup for which you can actually prove theorems about cluster algebras just by working with these lattices. So the question is, can you use extended weak order to construct these lattices and then understand affine type cluster algebras? So that's one of our motivating problems. Okay, and then there's a lot of open conjectures about biclosed sets. They're really like not well understood. So one is also by Matthew Dyer, and this was actually older than the lattice conjecture. So there's a notion of a reflection order, which is a total order on the positive roots, such that every order ideal is a biclosed set. And the question is, given a biclosed set, is it the order ideal of some reflection order? So that I did not actually define that because I figured I wouldn't have time, and I was right. And then of course, last question, we still don't know that the lattice property is true for all Coxeter groups. We only know the affine type. So that's a big open problem. So feel free to think about that. Thank you.
All right, yeah, let's give Grant a round of applause. That was a great talk. I learned a lot. Okay, are there questions? I guess, so you proved this like long-standing conjecture. Can you say a little bit about how you did that? Or is it
yeah. So for, actually I give the proof in the slides for type A.
Oh, okay.
So, but actually this is not the way that we proved it in general. Our proof is uniform for affine type. There's like a much stronger version of Dyer's lattice conjecture that basically is there's like you can define a closure operation, which is like the minimal closed set containing your set. And then it's like, we basically study properties of the closure operation for affine root systems, and you can actually reduce everything to type A2. This proof is not like on the archive, but it is in the FIFSAC extended abstract for the stuff I just talked about. So a bit hard to track down, but the proof is written in there.
Cool. Other questions? I guess I'm also curious about these combinatorial models that you talked about. So I think you kind of talked about the type A one. maybe? Or
I
is
talked
the-
about, yeah, this like A infinity one. I didn't actually get to, let's see, this. Oh, so this is the model for A n minus one. I'm sorry if you can hear that. I think they've been testing the fire alarm.
I didn't hear anything.
So the model is that you look at, so for this type A, the model is look at total orders of the integers that are translation invariant. So they satisfy this property. And basically the collection of those modulo something is the extended weak order for affine.
And is there something like similar for type B?
Yeah, so actually, yeah, for type C, there's something similar.
Oh, yeah, right.
Yeah, so B equals C infinite, but an infinite C is really what people usually consider VB. So yeah, for C, it's like a translationally invariant and invariant under sign change. Like if you reverse everything and negate everything, you get the same total order.
Cool. Other questions?
I think I finally formulated a question. So in the examples of these extended weak order, the posets appear to be self-dual. And it occurs to me that because of the geometry behind this, that might, is that always the case? And is that obviously always the case?
Yeah, so here is a proof. So the definition of a biclosed set is self-dual. Yeah, that looks right. So the definition of a biclosed set is self-dual, meaning that if a set is biclosed if its complement is biclosed. And so the duality for the poset is taking the complement of each biclosed set.
Okay. And does the finite part of your lattice get you, how big is the gap typically between the finite part of your lattice and the part, can you get so that neither the set nor its complement are finite, and how big is generally that part of the lattice?
Oh, yeah, that's a good question. So yeah, so in my pictures that doesn't happen. Oh, actually there is, sorry, there's one second. Okay, so here is an example of a set whose complement is, neither of these are finite.
Mm-hmm.
And you can even get more. So this is actually related to the theorem I mentioned about asymptotic behavior.
Mm-hmm.
So asymptotic behavior is just like how infinite is a given column of vectors. So every vector has like translates by delta, and you can ask, is it finite? Is like the set of things in that column finite? Is it infinite? Or is it complement finite?
Okay.
And so this is what we consider to be asymptotic behavior. And then there's like a nice parameterization of these asymptotic behaviors by faces of like the Cox arrangement. So here, of the finite type thing. So here is the Cox arrangement for the finite type thing. And yeah, so this face corresponds to that one. This face corresponds to that one.
Okay.
Yeah, any other questions?
I don't know if you already addressed it, but there was a link posted in the chat to what appears to be a FIBSAC paper.
Yes, that is my FIBSAC extended abstract where you can find the proof of the lattice property.
All right, let's thank Grant again for the great talk. And I guess we can stop the recording, and then if anyone wants to ask questions off the book.